Hello. Today we're going to talk about regression, which is a type of supervised learning where the output variable is numerical. First, let's recall what our data looks like. Remember, each row represents an observation and each column represents a variable. One of the variables is the output variable, and in this case, unlike in the previous case, it's numerical. In biology, there's many different numerical variables that you might want to be able to predict with a model. For instance, if you study humans or animals, you might be interested in height, weight, leg length, etc. If you study plants, you might be interested in yield of crops or number of leaves, stem length, flowering time, etc. If you study cell biology, you might be interested in things like cell size, cell density, level of fluorescently tagged proteins in images, proportions of cells expressing certain tagged proteins, etc. If you do transcriptomics, you might want to build a model to predict gene expression. So today, we're going to cover what defines a good regression model, then we'll review linear regression, which I'm assuming you have some level of familiarity with. Then we will talk about regularized regression, support vector regression, and random forest regression. So what defines a good regression model? Well, in classical statistics, you want to build a model that explains the data as well as possible. However, from the machine learning perspective, you want a model that is as useful as possible for making predictions. Recall from the previous weeks that in supervised learning, we often split our data into a training set, which we use to build a model, and then we test the model on a testing set, and we use that to measure the accuracy of the model. Well, we'll probably do the exact same thing here with regression. So let's review linear regression. In linear regression, you try to find a line that can be used to predict an output variable y given an input variable x. This line is called the line of best fits, and it's selected in order to minimize the mean squared error. In the mean squared error, you first find all of the residuals, which is the distance of the points from the line of best fit. You square that, and then you take a sum. The line of best fit formula will end up looking something like this, where A is the y-intercept and B is the slope. You can also do linear regression when you have more than one input variable. So, for example, if we have 4 input variables and 1 output variable, you can get a linear regression formula that looks like this. Now you have 1 intercept and 4 different slopes. We will call these slopes the set of coefficients. How do you interpret this formula? Well, if the coefficient is positive but small, then an increase in the x variable will mean a small increase in the y variable. If the coefficient is big and positive, then a small increase in the x variable will mean a large increase in the y variable. If the coefficients are negative, then the correlation will look like this. Hopefully, that was just a review. Next, we'll look at regularized regression. Sometimes you might have too many variables to do multiple regression analysis. For instance, if you have almost as many variables as observations, then you have a high risk of overfitting your data. In addition, if you have more variables and observations, then you can't even do standard linear regression anymore. One of the potential solutions to this is regularized regression. In regularized regression, you don't always pick the linear model that minimizes the mean squared error, but rather you also want to select a model that is simple in order to reduce the risk of overfitting. Regularized regression helps you balance the need to have a simple model and have a model that minimizes the mean squared error. I won't go into the math in detail. However, in general, L1 regularization, also called lasso, tends to force lots of the coefficients to be zero. That means you can drop them from the equation and end up with a simpler equation. In L2 regularization, many of the coefficients end up being small, so the slopes are less steep than in normal multiple regression analysis. However, there's now a balance that you have to strike between having a model that really minimizes the mean squared error and having a model that's simple. Recall that we take off our data and we split it into a training set, which we use to build the model, and a testing set, which we use to measure the accuracy of the model. Recall that we often take the training set and further divide it into a smaller training set and a validation set, and that the training set is used to build many alternative models. In regularized regression, the alternative models will have different levels of penalties for complexity. So for example, some of the models will penalize complex models a lot, and some will only penalize complex models a little bit. Some models will have a small penalty, and these models will be more complicated. However, they might have a lower mean squared error on the training set. Models with a large penalty will be very simple, but they'll have larger mean squared errors on the training set. However, this doesn't necessarily translate to having low mean squared errors on the validation set. However, what we really want is a model that is as predictive as possible on data that was not used to train the model. Once we have our alternative models, we can input the input variables of the validation set and get predicted output variables for which we can compare with the true output variables and find out the accuracy of the model. So, as we vary the penalty size, for each of the models, we can calculate the mean squared error on the validation set, which was not used to train the model. Then we can select the model that minimizes the mean squared error in the validation set and say that this is the most accurate model. Next, we'll cover support vector regression. Here I'm giving you an example of support vector regression in 2D, but the same principles apply when it's more than 2D, except instead of a line, you can replace that with a surface. Recall when we were working with classification, there was a method that we talked about called support vector machines. And as you recall, what support vector machines did was find a line that could be used to split the data into the two categories. So in this case, the blue category and the red category. And recall that this was a bit of a balancing act. We wanted the line to split the data into categories as accurately as possible, but we also wanted the points to be as far away from the central line as possible. And this gap is called the margin. So we wanted a big margin and a high accuracy. In support vector regression, we want to find a line of best fit such that the margin is as small as possible and there are as few points as possible outside the margin. So in this case, there's 2 points that are not within the range of the margin. Support vector regression works quite well when there's outliers compared to ordinary least squares regression, which is what we talked about in the previous slides. Next, we'll talk about random forest regression. Recall that when we were discussing classification, we used this table to form a decision tree that helped us decide whether a patient was healthy or sick. However, we can also imagine making a decision tree where the values that it produces are numbers instead of categories. Then, when you have a random forest, you can still have a lot of different decision trees. However, the output of each of these decision trees is now a numerical value. And instead of voting, you can just take an average of those numerical values, and that'll be your final output. So how do you choose a regression strategy? Well, linear regression has a bunch of benefits because it's easy to interpret. For example, you can look at the coefficients and learn how each of the variables relate to the output variable. Regularized regression is often necessary if there's too many input variables for normal linear regression. You want to choose L1 if you want to eliminate many of the input variables and have a smaller set of input variables. L2 regression is what you want to do if you don't want any individual variable having too big of an influence on the final prediction. Support vector regression is useful when you have outliers, because outliers often are very poorly handled by ordinary least squares regression. Random forest regression is useful because it allows for interactions between variables. There's also ways of allowing interactions between variables using multiple linear regression and support vector regression, but this often increases the number of parameters you need and the complexity of the model. So the main takeaways is that in machine learning, you want your model to be predictive, not just descriptive. And for this reason, we need a training set and a testing set, even when we do regression. Your model might be very descriptive of your data, but it could be overfit. In addition, you might want to penalize complex models in order to increase how predictive your model is. Also, there are alternative ways of doing regression that might work better on your data depending on how your data is structured. Previously, I mentioned lots of different numerical variables that you might want to predict as a biologist. I'd like to focus on one of these, which is gene expression, because regression can be used in kind of surprising ways. For example, regression can be used to help infer gene networks. So in this case, imagine that each row is a different tissue or experimental condition, and each column is a different regulatory protein or gene. And all of the values in the table are gene expression values. You can imagine building a linear model such as this that takes as input the regulatory protein gene expression values and produces as output the gene expression value of the specific gene of interest. Using regularization, you can simplify the model to include fewer input variables. If you use a different technique like random forest, you can also filter out certain input variables using the variable importance metric. Finally, you can describe this simplified model in a network format. In this example, the final model only includes x1 and x3. So these can be represented as circles, and they can point towards A, which is the gene that we were trying to predict. So in the end, we get a little subnetwork. Now you can repeat this procedure for all of the genes in the network. So for instance, you could replace gene A with gene B, then gene C, and so on, and continuously add to this network. This is one of the predominant ways of actually inferring gene networks from gene expression data. So thank you. And next time, we'll look at unsupervised learning.